So I am going to conclude this session for this concept. See, whenever you are going to correct a balanced load with the number of turns in the primary winding of the TZ transformer is 0.866 times of the N1, then we can say the phase, the voltage across the secondary side terminals are always balanced nature. So if we give a balanced supply voltages, then for a balanced load, the load voltages are also balanced in nature and the load currents are balanced in nature and also the supply currents are also in balanced nature. Suppose if you give a unbalanced load with the same primary winding turns of TZ transformer as root 3 by 2 times of N1, then we can say that even though you are going to give a balanced supply voltages, the output voltages are also balanced, but the output line currents are unbalanced and the input line currents are also unbalanced for an unbalanced load. So now we are going to study in detail regarding the auto transformers. So in a transformers, if one winding current enters the dot terminal, then in another winding current leaves the dot terminal. This is the basic concept in the transformer. See, in a transformer, the two winding transformer, if in one winding the current enters the dot terminal, then in the other winding the current is going to leave the dot terminal. This is the concept in a transformer. So suppose if you take a small concept here, it is a two winding transformer or single phase transformer. The primary winding having a number of turns of N1 and the secondary winding is having a number of turns of N2. So this is the dot here, this is the dot here. If in primary, if the current is entering the dot, means in the secondary the current is going to leave the dot. So this is the thing that you are always have to remember. So this is the kV of this two winding transformer. So now E1 is the induced voltage across the primary side and E2 is the induced voltage across the secondary side. So E1 by E2 is equal to N1 by N2, and also I1 into N1 is equal to I2 into N2. So this is a sign convention. This is plus minus, this is plus minus. So this is basically a sign convention. This is the rule that you always have to held for true. So I1 is called as the rated current of the primary winding or N1 winding. I2 is called as the rated current of the secondary winding or the N2 winding. So what is the primary winding current, which is kV of the two winding transformer by E1, and what is the secondary rated current? I2 is equal to kV of the two winding transformer by E2. So by this we are going to get the rated current of the primary winding and the rated current of the secondary winding. So in a transformer, if the current is entering the dot in one winding, the current is going to leave the dot in the another winding. This is the for a transformer. Suppose now what I am going to do, basically I am going to rearrange the above single phase transformer into auto transformer. So if I am going to arrange the above single phase transformer into a auto transformer, so this is the N1 and this is the N2. So this is called as a plus minus. So we can say it is additive polarity because both are in the plus minus and plus minus. So it is called as a additive polarity. So now here I am going to apply voltage of VH. So this is the VH voltage and this is the VL voltage. So you can see clearly this is the primary side and this is the secondary side. So this is the N1 turns and this is the N2 turns. So now what is NH? NH means N1 plus N2 and NL is nothing but N2. So this high voltage side, the number of turns is N1 plus N2, and the low voltage side, the number of turns is N2. So therefore you can see clearly NH is equal to N1 plus N2 and NL is equal to N2. So this is the primary side and this is the secondary side. The current inside the N1 turns is I1, whereas if the current is entering the dot, which is I1, then the current is going to leave the dot as I2. So this is I2 and this is I1. So I am going to assume this as called as the IL current. So this I am going to assume it as IL current. Basically IL is nothing but I1 plus I2. I am going to assume this is IL. So this is IL means this is VL voltage and this is a VH voltage means this I am going to assume it as the IH current. So VH IH and VL IL. This is basically I1 and this is basically I2. So IL is equal to I1 plus I2. So this is the primary side and this is the secondary side of the auto transformer. So NH is equal to N1 plus N2 and NL is equal to N2. So now what is the auto transformer ratio? The auto transformer turns ratio is equal to it is the ratio of the NH by NL. So always NH by NL is the auto transformer transfer, we can say this is a turns ratio, which is equal to number of turns of high voltage by number of turns of the low voltage, NH by NL. So now basically NH by NL is nothing but VH by VL. Now we will go for the reverse process, which is IL by IH. So this is the thing that you always have to remember. The turns ratio of the auto transformer is nothing but NH by NL is equal to VH by VL is equal to IL by IH. Total power transfer. So what is the total power transfer? The total power transfer from primary to secondary is nothing but is equal to VL into IL. The total power transfer is equal to VL into IL is equal to VH into IH. So what is the total power transfer? Input power is equal to output power, because there is no losses in the winding. So therefore VH into IH is equal to VL into IL. This is the total amount of power transfer. Which is total power transfer is equal to VL into IL is equal to VH into IH. Then I can make this VL into IL into two parts. I can make this VL into IL into two parts, which is VL into, see, you can see clearly VL into IL minus IH plus VL into H. So if you do the addition of these two terms, still you are going to get VL into IL. Or we can say VH minus VL into IH plus VL into IH. So by this also you are going to get the same result. So you are going to get finally VH into IH. So VH into IH is equal to VL into IL. So you can write either in this format or either in this format. You are going to get the same result. So if you see in an auto transformer, the power is transferred by two ways. One is magnetically and the other is conductively. The magnetically power is equal to, see, if you want to find what is the power transferred magnetically, the magnetical power is equal to take the voltage across any winding and take the current across that winding. So here for this winding, the voltage is nothing but VL, the current is nothing but IL minus IH. So the voltage is VL and the current is IL minus IH. So do the multiplication, VL into IL minus IH. VL into IL minus IH. So this is called as the inductive power or magnetically coupled power. So then what is the conductive power? The total power minus this magnetically coupled power is nothing but conductive power. That is the meaning of this one. Or try to find the power in this one. So magnetical power. So this is the voltage of this term is nothing but VH minus VL and the current is IH. So VH minus VL into IH is the magnetically power transfer. So both is always equal. So this power is always equal to this amount of power. Always it is true. So no matter whether you go for this one or this one, you will get the same result. And also, if you want conductive power, then go for the overall power transfer minus magnetical power. You are going to get the conductive power. So VL into IL, it is called the total power transfer. Whereas VL into IL minus IH is equal to VH minus VL into IH. I have already told you this is the magnetical power transferred by the lower winding and this is the magnetical power transferred by the higher winding, the upper winding. So this is by the lower winding, and you can say N2 winding, and this is by N1 winding. Both are always same. This is called as the inductive power transfer. So this is called as the inductive power transfer. If you want conductive power transfer, just with the subtraction of these two terms, total power transfer minus inductive power transfer, we are going to get the conductive power transfer, which is equal to, in this case, if do subtraction, we are going to get VL into IH. So you can say basically VL into IH in both the cases. So VL into IH is called as the conductive power transfer. So we can write in another format also. VL into IH, we can write another format, which is VL into IL into IH by IL. IL cancels, you are going to get the same thing. So VL into IL into IH by IL is nothing but is 1 by A auto transformer. So therefore you can say VL IL by A auto transformer is called as the turns ratio of the auto transformer. So VL IL by, or you can say total power transfer by turns ratio of the auto transformer. We are going to get the conductive power transfer. So conductive power transfer is the ratio of the total power transfer by turns ratio of the auto transformer. So VL into IH is nothing but simply VL into IL into IH by IL. So IH by IL is nothing but this is inverse of the auto transformer turns ratio. So therefore VL into IL is called total power transfer. So total power transfer by turns ratio of the auto transformer is called as the conductive power transfer. So now figuring out the maximum kVA auto transformer when two winding transformer is reconstructed as the auto transformer. So figuring out the maximum kVA of the auto transformer when two winding transformer is a reconsidered as the auto transformer. Means copper weight is same. So we are going to reconfigure the two winding transformer as the auto transformer. Then what is the maximum rating of what is the maximum rating of the kV of the auto transformer we are going to figure out. So finding out the maximum kV of the auto transformer, whenever the two winding transformer is reconsidered as the auto transformer, means the copper weight is still the same. So now this is basically, you can see, this is called as the a single phase transformer. So primary winding and secondary winding. Let me assume this is a 10 kVA transformer. The voltage ratio is 1000 volt slash 200 volt. This is a kVA transformer. So kVA of the two winding transformer is equal to 10 kVA. Then what is the primary rated current, which is 10 kVA by 1000? We are going to get 10 ampere. Then what is the secondary winding rated current, which is 10 kVA by 200 volt? We are going to get 50 ampere. So the rated current of the primary winding is 10 ampere and the rated current of the secondary winding is 50 ampere. So now we will go for the additive polarity. So now we will see what is the things we are going to get. Additive polarity means plus minus plus minus. So if you do the addition, if you go for this process, it is called as the additive polarity, plus minus and plus minus. So this is called as the primary winding and this is called as the secondary winding. So this is called the primary winding and this is called as the secondary winding. So we are going to connect in the series fashion. So series AD, this is called as series AD. So now this is, I have already told you, this is a primary winding. So this voltage is 1000 volt and the secondary winding, this is called as a 200 volt. So the plus minus, which is also plus minus. So what is the overall input voltage, which is 200 volt? The addition of this 2 voltage. Whereas we are going to connect a load here. So we are going to connect a load here. The load voltage is equal to the voltage across this terminal is equal to 200 volt. See now, let me assume current entering the primary coil. This primary coil is I1R, which is equal to 10 ampere. If current is entering this dot, means the current is going to leave the dot here, which is equal to a value of 20, I2R is equal to 50 ampere. So if you apply the KCL at this junction, the outgoing current is a summation of the 50 plus 10 is 60 ampere. Then what is the kVA rating of auto transformer, which is 200 into 60, or 200 into 60 is nothing but 12 kVA, or 200 into 10 ampere. Then also you are going to get the 12 kVA. So this is the kVA rating of this auto transformer. So kVA rating of auto transformer is equal to 12 kVA. Then what is the inductive power transfer? Inductive power transfer is the, see, for this winding, what is the voltage? 200 volt. What is the current? 50 ampere. So 200 into 50. Or the voltage across this winding is 1000 volt. What is the current across this winding? It is 10 ampere. So 1000 into 10 is nothing but again same thing, we are going to get 10 kVA. So what is the conductive power transfer? Overall kVA rating minus inductive power transfer. So 12 kVA minus 10 kVA is nothing but 2 kVA. So this is the conductive power transfer. So what is the A auto transformer? I have already told you, auto transformer turns ratio is equal to higher, you can say higher voltage by lower voltage. What is the higher voltage? 200 volt. What is the lower voltage? 200 volt. So 200 by 200, we are going to get 6. So this is the value of the 6. So therefore this is the value of the turns ratio of the auto transformer is equal to 6 in this case. Suppose if we are going to shift the load to the upper coil. In the previous case we kept the load here, but now I am going to shift to the upper side and we will see what is going to happen. So same thing here, what I am going to do, this is a 1000 volt and this is a 200 volt. So what is the input voltage? 200 volt. But we are going to connect load across this coil, so its voltage is equal to 1000 volt. You can see it is also series AD connection. So now let me assume the current is, see the current, I am going to assume that current I1. Suppose this current is entering the dot here. What is the current entering the dot, which is in this 200 volt is nothing but current is here 50 ampere. So this is the current 50 ampere. Then what is the current is, so if you go close here, if you go for the circle, you are going, it is entering dot here. So it has to leave the dot here. How much? It is 10 ampere here. So 50 plus 10 is nothing but 60 ampere. Then what is the kVA rating of the auto transformer, which is equal to 1000 volt into 60 or 200 volt into 50, you are going to get the 60 kVA. What is the inductive power transfer? Across this winding, the voltage is 1000 volt and the current is 10 ampere. So 1000 into 10 is nothing but equal to, again you go for either this one also. The voltage is 200 and the current is 50. Still you are going to get the 10 kVA. And what is the conductive power transfer, which is overall kVA minus inductive power transformer, which is 60 minus 10 is nothing but 50 kVA. So what is the auto transformer turns ratio? Higher voltage by lower voltage, or higher turns by lower turns, or the lower current by higher current. So what is the higher voltage? 200 volt by lower voltage is 1000 volt, you are going to get 1.2, you are going to get as a 1.2 as a turns ratio. So now we are going to go for the subtractive polarity and we will see what is going to happen. Subtractive polarity means in the previous case just we have shifted this voltage to this to drop to downward and we will see what is going to happen. So now if I go for this connection and I will see what is going to basically happen. So if I go to the reverse process, it is called as a plus minus and plus minus. So both are opposite in nature. So plus minus means it is a series connection, plus minus and minus plus. So you can see clearly there is a reduction in voltage. So this is called as we can see series subtractive polarity. So this is plus minus 1000 volt, plus minus 200 volt. So what is the overall input voltage? So if you apply the KVL, we are going to get plus minus of 800 volt here, and this is plus minus of 200 volt. Load we are going to connect here basically. Then see, I am going to assume the current is entering this coil is as 10 ampere because the rated current. If it is entering means it has to leave the dot. So this is 50 ampere leaving the dot here. Then what if you apply the KCL at this junction, then definitely the incoming current should be 40 ampere. 40 plus 10 is only 50. So this is the current we are going to get, the load current. So the load voltage we know, the load current we know. So therefore the KVL rating of the auto transformer is equal to 200 into 40 or simply 800 into 10. You are going to get same 8 kVA. What is the inductive power transformer, which is 1000 volt into 10 ampere or 200 volt into 50 ampere. So you are going to get 10 kVA. What is the conductive power transformer, which is overall kVA minus inductive power transformer, which is 8 minus 10 is nothing but minus 2 kVA. So what is the turns ratio of the auto transformer? Higher voltage by lower voltage. Higher voltage by lower voltage, which is 800 by 200. So we are going to get 4 volt. 4 we are going to get. This is the turns ratio of the auto transformer. Higher voltage by lower voltage. So now for the subtractive polarity, just I shift the load from this to here. Now we will see what is going to happen. So here is a plus minus, plus minus. So if you apply the KVL, we are going to get plus minus of 800 volt. And we are going to connect load here. So parallel combination. So therefore this is plus minus 1000 volt. And if I am going to assume the current is entering the dot, which is 10 ampere, so current should leave the dot here, which is 50 ampere. It is going to leave the dot here. So if you apply the KCL at this junction, so therefore this is 50, this is 10 means we are actually 40 ampere. Then what is the KVL rating of auto transformer, which is 1000 into 40 or 800 into 50, you are going to get 40 kVA. What is the inductive power transformer, which is 1000 volt into 10 ampere or 200 volt into 50 ampere, we are going to get 10 kVA. What is the conductive power transformer, which is overall kVA minus inductive power transformer, 40 minus 10 is nothing but 30 kVA. So what is the turns ratio of the auto transformer? Higher voltage by lower voltage, or we can say simply the primary voltage by the secondary voltage. So this is the primary voltage by the secondary voltage. So basically it is a primary voltage by secondary voltage. 800 by 1000, we are going to get 0.8. So basically turns ratio of the auto transformer is equal to this VH by, this is called VH and this is VL. Then NH by NL or IL by IH. So this is the formula that you always have to remember. Auto transformer turns ratio is equal to VH by VL or NH by NL or IL by IH. So this is VH side and this is VL side. The turns ratio of the auto transformer can be lesser than 1 or greater than 1. So now listen carefully. Concept. Turns ratio. Turns ratio means the auto transformer turns ratio is equal to, I have already told you, VH by VL is equal to IL by IH is equal to NH by NL. I have already told this one. But what is the transformation ratio? Transformation ratio is the reverse of the auto transformer turns ratio. So transformation ratio is the reverse of the auto transformer turns ratio. Let's go for the reverse of this one. So VL by VH is equal to IH by IL is equal to NL by NH. It is equal to reverse of the auto transformer turns ratio. So turns ratio of the auto transformer is equal to VH by VL is equal to NH by NL is equal to IL by IH. Whereas the transformation ratio is the reverse of the auto transformer turns ratio, which is VL by VH is equal to IH by IL is equal to NL by NH is equal to 1 by auto transformer turns ratio. The turns ratio of the auto transformer can be lesser than 1 or greater than 1. So summary. Now what we have learned from this concept. So you can see clearly turns ratio of the auto transformer and the corresponding KVA rating of the auto transformer. So whenever the turns ratio is 6, you got the KVA rating as 12 kVA, and whenever the turns ratio is 1.2, then you got the KVA rating as 60 kVA, and whenever the turns ratio is 4, you got the KVA rating as 8, and whenever the turns ratio is 0.8, you got the KVA rating as 40. So this first two for the additive polarity and second for the subtractive polarity. So only in the additive polarity only you are going to get the maximum rating of the kVA of the auto transformer, and its value, turns ratio value should be nearly equal to 1. So you can see 1 point is nearly equal to 1. At this case only you are going to get the kVA rating as maximum. So this is the point that you always have to remember. So maximum kVA rating is going to occur in auto transformer for only additive polarity, and at the condition is the turns ratio should be nearly equal to 1. At that condition only we are going to get the maximum rating of the kVA auto transformer. So maximum kVA rating in auto transformer is possible in additive polarity, and the auto transformer turns ratio is close to 1. Only in this case only we are going to get. So maximum kVA rating in auto transformer is possible in additive polarity, and the turns ratio of the auto transformer is close to 1. So for same power weight in auto transformer and two winding transformer, what is the thing that we have learned or we are going to see? See, for same copper weight in auto transformer and two winding transformer, because just we have rearranged the two winding transformer into auto transformer with the same amount of copper, so copper weight is same. So for same copper weight in auto transformer and two winding transformer, always the kVA rating of the auto transformer is always greater than the kVA rating of the two winding transformer. And the copper loss is same because same amount of copper is there, and the same rated currents are going to pass in both the windings, primary and secondary. So copper loss is still the same, but the efficiency is going to get changes. So always for the same amount of copper weight in auto transformer and the two winding transformer, the kVA of the auto transformer is always greater than the kVA of the two winding transformer, and the copper loss is same in both the cases, in the two winding and also in the auto transformer, and the efficiency is going to get changes. So for same copper weight in auto transformer and two winding transformer, the kVA rating of the auto transformer is always greater than the kVA rating of the two winding transformer, and the copper loss is same in both the cases, and efficiency is going to get changed. I have already told you the turns ratio of the auto transformer is equal to VH by VL is equal to NH by NL is equal to IL by IH. This from primary to secondary side. Always turns ratio of the auto transformer can be lesser than 1 or greater than 1. Whereas the transformation ratio is the inverse of the turns ratio. It is VL by VH is equal to NL by NH is equal to IH by IL. So now you can go for the small formula. So listen carefully. The inductive power transfer is equal to, I have already told you, inductive power transfer is equal to, from the basic general equation, VL into IL minus IH. So VL into IL minus IH. So VL into IL minus IH. This is from the general expression. So therefore, if I take here IL as a common, so if I take IL as a common, then what I am going to do basically, if I take IL as a common, then I am going to get VL IL into 1 minus IH by IL. Or IH by IL is nothing but simply you can say VL by VH. So IH by IL is nothing but VL by VH. So therefore VL IL is nothing but again VL IL is nothing but VH IH. So therefore VH IH into 1 minus VL by VH. So you can go for any of this formula. This is basically from a general expression. So this is the formula that you always have to remember. Inductive power transfer is equal to the kVA rating of the two winding transformer when we connect rated load across the auto transformer. So therefore kVA of the auto transformer is equal to kVA of the load. So inductive power transfer. So inductive power transfer is equal to kVA rating of two winding transformer when we connect a rated load across the auto transformer, which is kVA of the auto transformer is equal to kVA of the load. So this is the thing that you always have to remember, which is the inductive power transfer is equal to the kVA rating of the two winding transformer when we connect a rated load across the auto transformer, which is the kVA rating of the load is equal to kVA rating of the auto transformer. So whenever you are going to connect the kVA rating of the auto transformer as a load, so if you are going to choose the load its rating is equal to kVA rating of the auto transformer, then the rated currents are going to pass. So whenever the rated currents are going to pass, then we can say the inductive power transfer at that condition is equal to the inductive power transfer at that condition is equal to the power, the kVA rating of the two winding transformer. So this is the thing that you always have to remember. So whenever you are going to connect a load, its kVA rating is equal to kVA of the auto transformer for this auto transformer, then definitely the amount of inductive power transfer is equal to kVA rating of the two winding transformer. See, you can see now you can see clearly the kVA rating of this two winding transformer is 10 kVA. So in the additive polarity, in the case one you can see clearly the inductive power transfer is equal to 10 kVA. Here also you can see the inductive power is equal to 10 kVA. The suppletive polarity also, the inductive power transfer is again 10 kVA for the first one. And for the second one also, the inductive power transfer is equal to 10 kVA, which is equal to the rating of the kVA of the 2-winding transformer. So what I am trying to say finally is, basically, if you are going to connect a load, its rating is equal to kVA of the auto transformer, then the inductive power transfer is equal to the rated kVA of this 2-winding transformer itself. So now let's discuss some more important things here. So the amount of inductive power transfer is equal to kVA rating of the auto transformer into 1 minus 1 by A, the turns ratio of the auto transformer. If you want connective power is equal to kVA rating of the auto transformer into 1 by turns ratio of the auto transformer, where K is called as the transformation ratio, which is the turns ratio of the auto transformer. So listen carefully, that kVA rating of the auto transformer is a summation of the inductive power and the conductive power. So if you do the addition of these two things, we are going to get the same thing, which is called as the kVA rating of the auto transformer. So 1 by turns ratio of the auto transformer is called as the transformation ratio. So these are the important points that you always have to remember. So inductive power is equal to kVA rating of the auto transformer into 1 minus 1 by turns ratio of the auto transformer, and the conductive power is equal to kVA rating of the auto transformer into 1 by turns ratio of the auto transformer. So if we add the inductive power and conductive power, we are going to get the kVA rating of the auto transformer, and the transformation ratio is equal to turns ratio, the inverse of the turns ratio of the auto transformer. Turns ratio of the auto transformer is equal to VH by VL is equal to NH by NL is equal to IL by IH, whereas the K is the inverse of this one. So we are going to get VL by VH is equal to NL by NH is equal to IH by IL. So now we are going to discuss some more important things regarding auto transformer. We are using the copper weight in order to get the both kVA as equal. So now see, the two-winding transformer is already there. So now I am going to reduce the amount of copper. So therefore, if I am going to reduce the amount of copper, I want to make both the kVA of the two-winding transformer and also the auto transformer both as same. Then what I should do? See, the copper weight is nothing but weight is equal to density into volume. So copper weight is equal to density is equal to volume, because density is equal to mass by volume. So mass is equal to density into volume. So copper weight is equal to copper density into volume. So copper weight is directly proportional to volume. Volume is nothing but area into length. So what is the value of length? Area is directly proportional to current, and length is equal to 2 pi r into the number of turns n. So 2 pi r into number of turns n. So therefore, it is directly proportional to current into number of turns. So current into number of turns is called as the MMF. So copper weight is directly proportional to MMF. So more is the MMF, more is the copper weight. This is the concept we are going to see here. So more is the MMF, more is the copper weight. So current density is equal to current per area. So now what we are going to do basically is, this is a two-winding transformer and this is a auto transformer. So you can see this is called as the primary winding and secondary winding. The primary winding has a number of turns as NH, and the secondary winding is going to have a number of turns of NL. So this is the dot and this is the dot. The current is going to enter the dot, the current is going to leave the dot. So this is IH and this is IL. So load 1 we are going to connect. This is called as a kVA rating of the two-winding transformer. So now I am going to remove this secondary coil itself. I am going to remove the secondary coil, means I have reduced the copper weight, because I am not going to use the secondary winding itself. I have removed it. Directly I give the connection here to the primary winding itself. So this is called as the auto transformer. Now the copper weight has been reduced. So now the copper weight of the auto transformer is reduced, because we are not even considered the secondary winding of the two-winding transformer. So now this is the number of turns as NH and this is the number of turns as NL. And if this is the current is IH and this is the current is IL, then what is the amount of this current, which is IL minus IH, because by KCL. If you add the IH plus IL minus IH, we are going to get IL. If this is NH, if this is NL, this will be NH minus L and NL number of turns. So same load we are going to connect for the two-winding transformer and the auto transformer. Then we will see this is a turn, we can say kVA of the auto transformer. So now we have to make both these as same KVA. The KVA of the two-winding transformer is equal to KVA of the other transformer is equal to the KVA of the load we are going to connect. So both the three things should be always same. The KVA of the two-winding transformer is equal to KVA of the auto transformer is equal to KVA of the load. So if you are going to reduce the copper, then it is possible to make the KVA of the two-winding transformer and the KVA of the auto transformer same. But if you are not going to reduce the copper, means definitely the KVA rating of the auto transformer is always greater than the KVA rating of the single phase transformer. Turns ratio of auto transformer is equal to NH by NL. So NH by NL. So what is the total MMF of the two-winding transformer? The total MMF of the two-winding transformer is equal to NH into IH plus NL into IL. But for a two-winding transformer, the primary MMF is always equal to secondary MMF. So therefore NH into IH is equal to NL into IL. Then what is the total MMF of a auto transformer, which is equal to NH minus NL into IH plus NL into IL minus IH. So total MMF of the auto transformer winding is simply you can see these turns as the number of turns above is NH minus NL and the current is IH. So NH minus NL into IH plus this number of turns is NL and the current here is IL minus IH. So therefore NH minus NL into IH plus NL into IL minus IH. So this is the turns ratio of the auto transformer. Then I want to find what is the copper weight of the auto transformer by copper weight of the two-winding transformer. I have already told you the weight is directly proportional to its MMF. So the copper weight in auto transformer by copper weight in two-winding transformer is equal to ratio of the total MMF in auto transformer by ratio of the total weight in two-winding transformer. It is equal to, I have already told you, the total MMF in auto transformer is equal to NH minus NL into IH plus NL into IL minus IH by total MMF of the two-winding transformer is equal to NH into IH plus NL into IL. So because I have already told you the copper weight is directly proportional to the MMF. So therefore copper weight in auto transformer by copper weight in two-winding transformer is equal to MMF, the total MMF in auto transformer by total MMF in two-winding transformer. So total MMF in auto transformer is NH minus NL into IH plus NL into IL minus IH by the total MMF in the two-winding transformer is NHIH plus NLIN. But now we have to do the simplification by assuming NHIH is equal to NLIL, and if we do simplification, finally we are going to get the copper weight in auto transformer by copper weight in two-winding transformer is equal to 1 minus 1 by turns ratio of the auto transformer. So this is the value that we are going to get. Then what is the turns ratio of the auto transformer? See, turns ratio of auto transformer is equal to NH by NL. So NH is always greater than NL. So therefore this is greater than 1. So inverse of this is less than 1. So therefore 1 minus is nothing but 1 minus anything is lesser than 1. So this overall value is lesser than 1. So therefore you can say the copper weight in auto transformer is lesser when compared to copper weight in two-winding transformer. So the turns ratio of the auto transformer is equal to NH by NL is always greater than 1. So this value is less than 1. So 1 minus anything is less than 1 is again less than 1. So therefore simply we can say that the copper weight in the auto transformer is lesser than the copper weight in the two-winding transformer, because we have not used the secondary winding itself of the two-winding transformer. So we can say the copper weight of the auto transformer is always lesser than the copper weight of the two-winding transformer. Then how much amount of copper is saved? If you want to find how much amount of copper is saved, means the copper winding in two-winding transformer minus copper weight in the auto transformer by copper weight of two-winding transformer into 100. So how much amount of copper is saved? The amount of percentage of copper winding saved is nothing but the amount of copper in two-winding transformer minus the amount of copper in auto transformer by the amount of copper in two-winding transformer into 100. So if we do simplification, we are going to get finally 1 by A auto transformer into 100. So 1 by turns ratio of the auto transformer into 100. So this much amount of copper is saved with the help of using the auto transformer. So by using auto transformer, this much percentage of the copper is saved. So the percentage of copper saved is equal to the copper weight in two-winding transformer minus copper weight in auto transformer by copper weight in two-winding transformer into 100. So if this simplification, we are going to get finally that is 1 by turns ratio of the auto transformer into 100. So you can see clearly the turns ratio is nothing but it is always greater than 1. So anything by greater than 1 is again, you can see clearly you are going to get some percentage value we are going to get. See, as copper reduces, what is going to happen? As copper reduces, the resistance will decrease. As copper reduces, the resistance will decrease. As resistance decreases, the voltage drop decreases. As the voltage drop decreases, the copper loss decreases. As the copper loss decreases, the core loss decreases because volume of core is less. So efficiency is increases. So as copper decreases, the resistance decreases. Then the voltage drop is also going to get decreased because V is directly proportional to R. As R decreases, voltage drop decreases. So therefore the copper loss is also less because less amount of copper. So core loss is also decreases because volume of core is less because here we are going to use only half of the core, not full core. So because of that, volume of core is also less. So therefore core loss is also decreases. So therefore the loss of decreases means efficiency is increased. So now we can say that with the help of this one, as the copper decreases, the resistance decreases, so voltage drop decreases, so copper loss decreases, so core loss also decreases because we need only half of the core, not the full core. Therefore, volume of core is also less. So therefore, the core loss decreases. If the loss of decreases means efficiency will increase. So the copper loss of auto transformer by copper loss in twinning transformer is equal to the voltage drop in auto transformer by voltage drop in twinning transformer is equal to 1 minus 1 by turns ratio of the auto transformer. So remember this important point. See the copper weight. So it can have another formula also. The copper weight in auto transformer by copper weight in twinning transformer is equal to copper loss in auto transformer by copper loss in twinning transformer is equal to voltage drop in auto transformer by voltage drop in twinning transformer is equal to 1 minus 1 by turns ratio of the auto transformer. So listen carefully. The copper weight of auto transformer by copper weight of twinning transformer is equal to copper loss in auto transformer by copper loss in twinning transformer is equal to voltage drop in auto transformer by voltage drop in twinning transformer is equal to 1 minus 1 by A auto transformer. It is called the turns ratio of the auto transformer. So now for these auto transformers, I will discuss some more important points. Step down auto transformer means stepping down the voltage. So you can see the core is reduced because with the help of this only half of the core is required. So core is reduced means core loss is also decreases. So therefore this is the amount of core. For this only one winding we are going to use both as a primary and the secondary. So therefore here the primary voltage is V1, the secondary voltage is V2, the primary current is I1, the secondary current is I2, the number of turns is N1, here the number of turns is N2. So by this help we can say the current in this N2 turns is simply I2 minus I1. So now V1 by V2 is equal to N1 by N2. So V1 by V2 is equal to N1 by N2. So therefore V2 is equal to V1 into N2 by N1. So you can see clearly V2 by V1. So V2 by V1 is equal to N2 by N1 is equal to I1 by N2. So this is called the transformation ratio. This is called the transformation ratio. This is called the transformation ratio here. So now I have already told you the copper weight in twinning transformer minus copper weight in auto transformer by copper weight in twinning transformer into 100 is equal to 100 into K. Where K is called as a transformation ratio. So K is called the transformation ratio means simply we can say that K is nothing but this inverse of the auto transformer. So I have already told you it is the inverse of the turns ratio of the auto transformer. So therefore we can say this is called as the amount of copper saving. So this is called as the amount of copper saving. So therefore the percentage of copper saving is equal to copper weight in twinning transformer minus copper weight in auto transformer by copper weight in twinning transformer into 100 is equal to, we can say 100 into K, or this is equal to 100 by turns ratio of the auto transformer. So K and turns ratio of the auto transformers are inversely proportional. So transformation ratio is equal to 1 by turns ratio of the auto transformer. I have already told this one. This is called as the percentage saving pattern. So this is called as the percentage saving pattern. Always the turns ratio of the auto transformer can be greater than 1 or lesser than 1. Only I have told you. So the turns ratio of the auto transformer in this case it is NH by NL. So the turns ratio of the auto transformer here is equal to N1 by N2. It is always higher than 1. So then what is the K value? The transformation ratio which is N2 by N1 is N2 by N1. It is less than 1 here. The turns ratio of the auto transformer is equal to N1 by N2. It is always greater than 1. But the transformation ratio is reversed. It is N2 by N1. It is always less than or equal to 1. Similarly, for the step down auto transformer. So for step down auto transformer, you can see clearly here. This is only one coil we are going to use for both primary and secondary. So supply voltage is V1, the supply current is I1, and the number of turns here is N1, then the number of turns is N2, and this is the supply, this is the load current is I2, and the load voltage is V2. If this is I1, this is I2, then the current here, I am going to current in the downward direction, which is nothing but I1 minus I2. So if you apply the KCL, we are going to get I1 is equal to I2 bar plus I1 minus I2 bar. So we are going to get same thing. So V2 by V1 is equal to N2 by N1 is equal to I1 by I2 is equal to, here this is called as a transformation ratio. This is called as a transformation ratio. Then you can see clearly here K is always greater than 1 because N2 is greater than N2 is always greater than N1. So K is always greater than 1 here. And I already told you, if you want to find what is the percentage amount of copper save, which is the amount of percentage copper save is equal to copper weight in chlorine transformer minus copper weight in auto transformer by copper weight in chlorine transformer into 100 is equal to 100 by turns ratio of the auto transformer. All these things I have already told you. So 100 by turns ratio of the auto transformer. So 100 by turns ratio of the auto transformer. So always the turns ratio of the auto transformer is the inverse of the transformation ratio. All these things I have already told in this concept only. So this is the concept that you always have to remember. The turns ratio of the auto transformer is always the number of turns of higher by number of turns of lower. So this is the formula that you always have to remember. And its value, the overall value, the percentage value always lesser than 100. So denominator should be always greater than 1. That is the thing you can do it very simple. So this is the percentage of saving copper. Three-phase winding connection. So now we will discuss about the three-phase winding connection. A used for the HV winding and small a is used for the LV winding. So calculators we are going to use for the HV winding and the small letters we are going to use for the LV winding. It is a basic notation. This is the notation that we are going to use for the three-phase winding connection. So the capital letters are used for the HV winding and the small letters we are going to use for the LV winding. So now the star connection. The star connection, see, this is a star connected load, or you can say star connection of any type, either it can be source or it can be a load. So let me discuss in general regarding the star connection. So this is a star connection. You can see clearly that these all the one common point. See, there is a one common point between each and every wire. So this we are going to connect it to a common point and we are going to call it as a neutral. So this is called as a star connection. See, you can see basically it has a turns of A to A1, B to B1, C to C1. So this point we are going to take it outside is called as the point A. This point we are going to take it outside and we are going to call it as B. And this point we are going to take it outside and we are going to call it as C. Or this is also we can draw in another fashion also, which is like this. This is A to A1, B to B1, C to C1. So J1, B1 and C1 we are going to join together and we are going to call it as the neutral point, and the remaining terminals we are going to take outside and we are going to call it as the A, B and C. Same as this one, A1, B1, C1 we are going to join together and we are going to call it as the neutral, and the remaining points we are going to take it outside like A, B and C. So in the another fashion also we can draw it, even like this also we can draw. See, this is the terminal of A to A1, B to B1, C to C1. So join all the common points of A1, B1, C1 to a common point is called as the end, and take the remaining points outside, which is called as the A, B and C. So you can see clearly you can draw either this one or this one or this one. Each and everything is same. So therefore simply we can say that A1, B1, C1 we are going to join together. That point is called as a neutral, and we are going to take the remaining points outside and call it as the A, B, C. So you can draw either in this fashion, or either you can draw in this fashion, or either you can draw in this fashion. These are the three different forms of writing the star connection. In the same manner, now we will discuss for the delta connection, the different types of connection. So similarly, you can see clearly that A1, A2, B1, B2, C1, C2, C1, C2. So now A2 is joined to C1, C2 is joined to B1, and B2 is joined to A1. So this joining point we are going to take it outside and we call it as A. This joining point we are going to take it outside and call it as B. and this joining point we are going to take it outside and call it as the C. So this is called as the delta connection. So you can draw in another fashion also. A to A1, B to B1, C to C1. So see carefully, A1 is joined to B2 and B1 is joined to C2 and C1 is joined to A2. So this is the joining we are going to do like this. So A1 is joined to B2, B1 is joined to C2 and C1 is joined to A2. And we are going to take the point C, A2 and C1 joint we are going to take it outside and call it as A. Similarly, A1 and B2 joint we are going to take it common point and take it outside, this called as B. Similarly, B1 and C2 joint we are going to take it outside and call it as a C. So you can write either in this fashion or in this fashion also it is same. Similarly, you can write another fashion also, which is A1, A2, B1, B2, C1, C2. I have already told you we are going to join the A1 and B2. So A1 and B2 is joined. Similarly, B1 and C2 we are going to join, and then C1 and A2 we are going to join. So we are going to join like this, and then A2 and C1 common point we are going to take it outside and call as A, and then A1 and B2 that common point we are going to take it outside and call it as B. Again B1 and C2 the common point we are going to take it outside and call as the C. So these are the three different types of connections of a delta connection. So this table is very much important. You have to remember this table. So these are the only types of connections which are possible. These are the types of connections which are only possible. The connections possible are, we can say, in a star-star. In a star-star, you can get either 0 degree or either 180 degree. 0 degree is also called as a 12 o'clock, and 180 degree is called as a 6 o'clock. So in a star connection, you can get either, in a star-star connection, you can get either 0 degree or 180 degree. So 0 degree is called as a 12 and 180 degree is called as a 6 o'clock. So this is 12 o'clock and this is 6 o'clock. Similarly, in delta also, you can get either 0 degree or 180 degree. So 0 degree is also called as 12 o'clock and 180 degree is also called as 6 o'clock. So in a star-star, you can get either 0 degree or 180 degree. In delta you can get either 0 degree or 180 degree. So 0 degree means 12 o'clock, 180 degree means 6 o'clock. Similarly, in a star delta, you can get either plus 30. This plus 30 means another will be minus 30. Again, minus 30 and plus 150. So plus 30, minus 30. Minus 150, plus 150. So we can say it is plus 30 means minus 150. Here it will be minus 30 and plus 150. So we can get either of this one. So we can say plus 30 means it is at 11 o'clock. Plus 30 means 11 o'clock. Minus 150 means it is 5 o'clock. Minus 30 means it is 1 o'clock. Plus 150 means it is 7 o'clock. Again, in delta star, the star delta we have seen. Now, delta star. In delta star also we can get plus 30 minus 150. So here, minus 30 and plus 150. So plus 30 means I have already told you 11 o'clock. Minus 150 means 5 o'clock. So minus 30 means 1 o'clock. Plus 150 means 7 o'clock. So these are the type of connection you are going to get. So total how many connections are possible? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So only these 12 types of connections are possible. Only these 12 types of connections are possible. So you can see clearly in a star, you can get either 0 clock or either you can get 180 clock. So in delta also you can get either 0 degree or 180 degree. So 0 degree means 12 o'clock, 180 degree means 6 o'clock. The star delta you can get plus 30 minus 150, minus 30 plus 150. So plus 30 means we can say 11 o'clock. Minus 150 means it is 5 o'clock. So minus 30 means it is 1 o'clock. Plus 150 means it is 7 o'clock. Similarly, delta star you can get plus 30 minus 150 minus 30 plus 150. So plus 30 means 11 o'clock. Minus 150 means 5 o'clock. Minus 30 means 1 o'clock. Plus 150 means 7 o'clock. So these are the types of connections only you can possible. Only 12 types of connections are possible. Star, delta. Star means you can get 0 degree or 1 degree. Delta you can get 0 degree or 1 degree. In star delta, you can get plus 30, minus 150, minus 30, plus 150. In delta star, you can get plus 30, minus 150, minus 30, and plus 150. Only these type of connections are possible. So we are going to use one general convention, HV phasor. HV phasor means high voltage phasor, line to neutral voltage. So we are going to choose the line to neutral voltage, and it is represented by the minute hand. Minute hand. It is fixed at 12 a.m. So minute hand we are going to fix it at the 12 a.m. So 12 o'clock. At 12 o'clock we are going to fix the minute hand. Whereas the LV phasor is called as the line to neutral voltage. It is represented by the hour hand. So listen carefully. HV phasor means we can say high voltage phasor. High voltage phasor means we are going to generally choose only the line to neutral voltage, or simply we can say phase voltage. So line to neutral voltage is also called as a phase voltage, and we are going to see HV voltage means it is a high voltage, means in a clock which hand is very high, it is a minute hand. So minute hand we are going to fix it at always 12 o'clock. And LV phasor means we can say low voltage phasor. It is basically line to neutral voltage, means we are going to consider only the phase voltage. LV low voltage means in a clock which is very low in size, which is called as the hour hand. So hour hand we are going to vary, but the minute hand is always fixed at the 12 o'clock. So this is a convention that we are going to choose. So high voltage phasor means line to neutral voltage. We are going to choose the minute hand, and we are going to fix it at the 12 o'clock. Whereas the low voltage phasor is also used as the line to neutral voltage, and we are going to choose as the hour hand. It is going to go as per the convention, as per the requirement. So phase voltage of primary and secondary must be either in same phase 0 degree or in opposite phase 180 degree only. So phase voltage of primary and secondary must be either in same phase or in opposite phase 180 degree only. So phase voltages of the primary and secondary can be either in same phase or can be in opposite phase. Only these two are possible. Only these two are possible. Either they can be 0 degree or either they can be 180 degree only. So we can see clearly phase voltage of primary and secondary. So phase voltage of primary and secondary must be either in same phase or in opposite phase 180 degree only. Only these are possible. So this is the general way to remember the connections. Star star. Star star means you can get 0 degree or 180 degree. Star delta means you can get plus 130, minus 150, minus 30, plus 150. And delta star means you can get plus 30, minus 150, minus 30, plus 150. Delta means you can get either 0 degree or 180 degree. So plus 30 means it is plus 30. If you see plus 30, it is 11 o'clock. So minus 30 means it is at 1 o'clock. Minus 150 means it is 5 o'clock. Plus 150 means it is at 7 o'clock. So this is the easy thing that you have to remember. So plus 30 means it is 11 o'clock. Minus 30 means it is 1 o'clock. Minus 150 means it is 5 o'clock. And plus 150 means it is 7 o'clock. So now you will see each and every convention, each and every connections in a very detailed manner. So according to the British convention, we give supply and take supply from A to B to C to and small a to small b to small c2. So according to the British convention, we give supply and take supply and from A to B to C2 and small a to small b to small c2. So this is basically a British convention. So we are going to give supply and we are going to take the supply from A to B to C2 or small a to small b to small c2. So now we will discuss generally each and every 12 connections. All these 12 connections now we are going to learn one after the another in a very detailed manner. So star star. So you can connect the star star. Either I have already told you can connect the star star connection in either 0 degree or you can connect in a 180 degree or you can say 12 o'clock or 6 o'clock. So now we will see each and everything. So star star 0 degree or it is also called as the star star 12 o'clock. So now we see this is called as the HV winding. HV winding, I have already told you the HV winding. The HV winding are denoted by the high, we can say capital letters, whereas the LV winding is represented by the small letters. So A1, A2, B1, B2, C1, C2, A1, A2, B1, B2, C1, C2. So now, as I have already told you, I am going to give supply to the A2, B2, C2 and take supply from small a to small b2 and small c2. So I need to go for the star connection. Star connection means this A1, B1, C1, I am going to connect to a common point. It is called as a neutral. Similarly, small a1, small b1 and small c1, I am going to connect to a common point. It is called as the small m. So this is called as a star connection and star connection. So now we will see what is the 0 degree. So here A to A1. So this is called as a to A1. So A to A1. See, arrow we have to keep wherever we are taking the, we are giving the supply. So at A2 we are giving the supply. Similarly B1, B2. So this is called as a B1, B2. So B1, B2. So B1, B2, here we are going to give supply to B2. So take arrow at B2. And similarly C1, C2. So C1, C2, this is C1 and this is C2. We are going to give supply at C2. So take this one as C2. Take the arrow at the C2. So this A1, B1 and C1 we are going to join it to a common point. Then we are going to call it as the neutral. So this is the way that you always have to remember. Similarly here also, say if this is A1, A2, here also small A1, A2. They are in 0 degree or they are in 1 degree phase shift. This is the common thing. So A1, A2, then comes the B1, B2, then comes the C1, C2. Because it is in phase with B1, B2, this C1, C2 is phase with the C1, C2. So here also we are going to keep arrow at the A2, B2 and C2. So keep arrow at A2, B2 and C2. Join the A1, B1 and C1 to a common point is called as a neutral. So this is a neutral. So now we have to go for the line to neutral voltage. Here A to and N. So line to neutral voltage means A2 to N. This is called as a line to neutral voltage. Here also A2 to small n. This is also line to neutral voltage. So simply we can say that voltage between the A to N and B to N, both are having the same frequency and the phase angle between them is 0 degree. So therefore we can say it is said to be a 0 degree. You always have to calculate the phase angle between the line to neutral voltage of the HV winding and the LV winding. So now I have already told you high voltage phasor. High voltage phasor is always fixed at the 12 o'clock, which is the minute hand. Because the LV phasor we are going to make it as an hour hand. We are going to move it as per the circumstances. So both are in phase. So hour hand is also at the same phase with respect to minute hand. So therefore we can say this is called the 12 o'clock. So now we are going to learn about in a star we are going to learn about the other connection which is called as a 180 degree. So 180 degree is also called as a 6 o'clock. So now we will see this one, how to do this one. So same thing I already told you A1, A2, B1, B2, C1, C2. So A2, B2 and C2 give the supply and do the common connection of the A1, B1 and C1 as a neutral point. Similarly, take the another winding of here. I have already told you A1, A2, B1, B2, C1, C2. So now instead of taking supply from A to B to C2, take the supply from small A1, small B1 and small C1. So now do the common connection of this A to B2 and C2. So this is the point that you always have to remember. Instead of taking supply from A to B to C2, I am taking from supply from A1, B1 and C1, and I am going to do the common connection of this A to B to C2 as a neutral point. So now we will see what is going to happen. As I already told you, A1, A2, so this is A1, A2, this is B1, B2, this is C1, C2. So A1, A2, B1, B2, C1, C2. I am giving supply to A2, B2 and C2. So keep the arrows at that point, A2, B2 and C2. So this A1, B1, C1 are joined to a common point. It is called as a neutral. So this is called as a neutral point. Similarly here also, same thing we have to do. So A1, A2, B1, B2, C1, C2. So this is A1, A2, B1, B2. So same, take in same phase, A1, A2, B1, B2, C1, C2. But here you have to do something. You have to shift it. You have to shift the A1, A2 in this manner. So you have to shift actually this A1, A2, B1, B2, C1, C2. So just to shift this vector to this side and shift this vector to above and shift this vector to downward, because we have to connect the A2, B2 and C2 to a neutral point. So A2, B2, C2 we are going to connect to a neutral point, which is called as N. And we are taking supply from small a1, small b1 and small c1. So keep the arrows at that point, a1, b1 and c1. So listen carefully. Here this is a1, a2, b1, b2, c1, c2. So we have to do connection of a2, b2 and c2. So just shift here, we are going to get a1, a2, and just to shift this point above, so we are going to get b2, b1. Just shift downward here, we are going to get c2, c1. and join these common 3 points. We are going to get a neutral point N and take the arrows at the supply points A1, B1 and C1. So now you can see clearly. That A to N, the voltage between the A to N and the voltage between the A1 N, both are of 180-degree phase shift. So they are having a phase shift of 180 degree. So we can say this simply. This is called as a 180-degree phase shift. Now to always consider the phase voltages or line to neutral voltages only. So therefore, the angle between the A to A1 and A1 and A2. So we can say clearly this angle is nothing but 180 degree. So therefore, we can see the angle between the A to N or A1 N. So therefore, we can say it is a 180-degree phase shift. So therefore, always I have already told you HV phasor is fixed at the 12 o'clock and LV phasor is a overhead and HV phasor is a minute hand. So therefore, this is our HV phasor. So we are going to fix it at the 12 o'clock. And here there is a 180-degree phase shift. 180 degree means the LV winding we have to give a phase shift of 180 degree means we are going to get a 6 o'clock. So this is a 6 o'clock representation. So now we are going to discuss the another connection delta. In that we are going to discuss about the 0 degree is also called as a 12 o'clock. So now I have already told you A1, A2, B1, B2, C1, C2. Then A1 we are going to connect to B2, B1 we are going to connect to C2 and C1 we are going to connect to A2. So A1 connected to B2, B1 connected to C2 and C1 is connected to A2. So this point we are going to take it as A, this point we are going to take it as B and this point we are going to take it as C. Similarly A1, A2, B1, B2, C1, C2. Similarly A1 is connected to B2, B1 is connected to C2 and C1 is connected to A2. This point I am going to take it as A, B and C. So now we will draw the phasor diagram to see each and every thing. As I have already told you here A1, A2. So this is A1, A2. And what is B1, B2? So B1, B2. So I have moved it upward. So I have moved it upward means I am going to get like this. Again C1, C2. So C1, C2. So just I have shifted here in this manner. So I am going to get a triangle. So now if you see clearly A1 is connected to B2. So A1 is connected to B2. And B1 is connected to C2. So B1 is connected to C2. And C1 is connected to A2. So C1 is connected to A2. And we are going to do supply A2, B2 and C2. So keep the arrows at the points. So keep the arrows at the A2, B2 and C2. So this is the way we are going to get. So these are basically line voltages. So we need a phase voltage. So phase voltage means take in the middle a neutral point. So take in the middle a neutral point and join a line from this neutral point to this one of this vector for one of this point which is A2. So draw line. So we are going to get in this fashion. Similarly here now for this one also same thing A1, A2, B1, B2, C1, C2. So just this is A1, A2. So now shift the B1, B2 to upward. You are going to get in this fashion. Again C1, C2 just shift it like this. You are going to get this one. Here also A1 and A1 is connected to B2. So A1 is connected to B2 and B1 is connected to C2. So B1 is connected to C2 and C1 is connected to A2. So C1 is connected to A2. Again these are the line voltages but we need a phase voltage. So therefore from the middle point take a neutral point and take from here to this point A2. So take this point we are going to get like this because we are going to take supply from A2. So take this point up to here because we are going to supply to A2 and take supply from A2. So therefore take at that particular point. So take at that particular point. So now we are going to see what is the phase shift between them. So they are same phase. They are in same phase with respect to each other. So HV winding is always shown by the minute hand and is fixed at the 12 o'clock. And the LV phasor we are going to represent by hour hand. It is a variable. So we can see clearly both are in the same phase. Line to neutral voltage are same phase. So we can say it is a 0 degree. The voltage between the A to N and the voltage between A to N both are having the same phase with 0 degree. So we can say it is a 12 o'clock. So now we will discuss the delta 180 degree or we can say delta 6 o'clock. So you can say clearly A1, A2, B1, B2, C1, C2. So A1 is connected to B2, B1 is connected to C2 and C1 is connected to A2. This is A, this is B and this is C. So here also what we are going to do basically now here. So now we are going to do the connection in a different manner. So now we are going to change the connection of this winding. Of this flow winding we are going to change the connection. In the previous case we have given for A1, B2, B1, C2 and C2, A1 and take supply from here. But now we will do the reverse connection, which is A2 connected to B1, B2 connected to C1, and C2 is connected to A1, and we are going to take supply from A1, B1 and C1. So this is the reverse connection of the previous case, and now we will see what is going to happen. So now, as I already told you, A1, A2, P1, B2 and C1, C2. They are A1, A2, P1, B2, C1, C2. They are going to have a phase difference of 120 degree there. So this A1, A2, I am going to keep it here. But B1, B2, I am going to move it outward. So I am going to get here B2 and this is B1. C1, C2, I will shift here. I am going to get like this. So now A1 is connected to B2. So A1 is connected to B2. And B1 is connected to C2. B1 is connected to C2. And C1 is connected to A2. So C1 is connected to A2. So you are going to get a triangle. And the middle point you are going to take it as a neutral point. And take a line from, because we are taking supply from A2. So take a line from N to this A2 point. We are going to take a vector. This is called as a phase voltage. So now we are going to draw the another vector of this one, of this vector diagram of this LV winding. So if you see clearly, here also A1, A2 is there. So here also A1, A2. So this is B1, B2. This is C1, C2. So A1, A2, B1, B2, C1, C2. So this is A1, A2. Now B1, B2. So this is called B1, B2. But B1 is connected to A2. So I am going to shift it here in this manner. Therefore, this is actually B1, B2, right? B1, B2. So B1, B2, I am going to shift it here. So this is B1, B2. And similarly C1, C2. So this is C1, C2. So this is C1, C2. C1, C2. This is C1, C2. I have done it here in this fashion. So you can see clearly A2 is connected to B1 and B2 is connected to C1 and C2 is connected to A1, and also take the arrow at the where we are going to take the supply A1, B1 and C1. Take the arrows at the A1, B1 and C1, and now take the neutral point, and we are taking supply from A1. So we are taking supply from A1. So draw a straight line. So draw a straight line up to a point A1. So therefore you can see clearly that for taking supply from A1, so up to point A, you have point A1, you have to draw a vector from neutral to here. So you can see clearly the phase angle between them is nothing but 180 degree. Therefore you can see clearly the phase angle between the A2N and A2N, A1N are nothing but they are having a phase difference of 180 degree. So we can say they are 6 o'clock. So our estimated angle is represented by the HV phasor. It is always fixed at 12 o'clock. And LV phasor is represented by the hour hand. It is a variable. It is mode as per the angle between them. So 180 means it is also called as the 6 o'clock. This is basically a 6 o'clock. So now we are going to discuss the star delta. In the star delta we are going to discuss the plus 30. Plus 30 degrees we are going to discuss. So plus 30 is also called as the 11 o'clock. So plus 30 is also called as the 11 o'clock. So now we will see this one. So HV winding A1, A2, B1, B2, C1, C2. So here HV winding we are going to connect in a star connection. So A1, B1, C1 we are going to give a star connection. Common point as neutral. And we are going to give supply to the A2, B2 and C2. Similarly, for this winding, we can see clearly A1, A2, B1, B2 and C1, C2. Here we have to connect in the delta fashion, and going to connect like this A2, B1, B2, C1 and C2, A1. And I am going to take supply from A2, B2 and C2 as A, B and C. So now we will see what is the vector diagram of the HV winding and the LV winding. As I have already told you, A1, A2, B1, B2 and C1, C2. So A1 is connected to B1 and B1 is connected to C1. So A1, B1, C1 are connected to a common point of N. So join them, and we are going to give supply to the supply to the A2, B2 and C2. So keep the arrows on the A2, B2 and C2. So we are going to get this phasor diagram, and this is the neutral point N. So now we are going to draw the phasor diagram of the LV winding. So now we are going to draw the phasor diagram of this LV winding. As I have already told you, this is A1, A2, this is B1, B2 and this is C1, C2. So now I am going to shift this B1, B2 to this side and C1, C2 to this side. So we are going to get a triangle. So now you can see clearly A2 is connected to B1 and B2 is connected to C1 and C2 is connected to A1. So we are going to get everything in this manner. And we are taking supply from A2, B2 and C2. So keep the arrows at the A2, B2 and C2. So keep the arrows at A2, B2 and C2. So we are going to get this one. But these are the line voltages, but not phase voltages. So at middle, take a point neutral and draw a line between. We are taking from A2, so keep that A2. So line up to A2. So this is the thing that we are going to get. So if you try horizontal line, it is having a exit of 30 degree. So we can say it is leading this voltage by 30 degree. So therefore this is leading. So this one is a plus 30 because it is leading. So this is leading this one. So this one is a plus 30 degree. So plus 30 degree. This one is a plus leading. So therefore the angle between the A2N and the A2N is nothing but plus 30 degree because the LV winding phase voltage is leading the phase voltage of the HV winding. So leading means we have to go in this side, lagging means we have to go on this side. So leading means this side, lagging means this side. Because here HV phasor is always fixed at this point. HV phasor is always fixed at this point. So LV phasor only we have to move. So it is leading. It is leading means here. It is leading means here. Lagging means this side. Leading means this side. So therefore it is leading. So leading by plus 30 degree. So this is called as a plus 30 degree. So plus is going to represent that LV winding is leading the HV winding by plus 30 degree. So plus 30 is simply just called as the 11 o'clock. So now we'll discuss the in the star delta another type of correction which is minus 150 degree. So minus 150 degree is also called as the 5 o'clock. So now we'll see each and everything in detail. So same thing, HV winding is connected in the star connection and the LV winding is connected in the delta connection. So therefore you can see A1, A2, B1, B2 and C1, C2. So A1, B1 and C1 we are going to join together to a common point of N and we are going to give supply to the A2, B2 and C2 terminals. Similarly, here LV winding we are going to give the connection in a reverse manner of the previous case. So we are going to give just a reverse connection when compared to the previous case. So now we are giving from A1, B2, B1, C2 and C1, A2 and we are going to take supply from A1, B1 and C1 as A, B, C. So now we are going to draw the vector diagram or the phasor diagram of these both windings. So you can see clearly this is A1, A2, B1, B2 and C1, C2. So A1, B1 and C1 we are going to join together to a common point as neutral N and we are going to give supply at A2, B2 and C2. So take supply from A2, keep arrow from at A2, B2 and C2. So you have to take this one. Now I am going to draw the phasor diagram of this LV winding. So see clearly this is A1, A2. So this is A1, A2, B1, B2 and C1, C2. So A1, A2 keep it like this. B1, B2 just move it upward and C1, C2 just shift it like this. We are going to get a triangle. So A1 is connected to B2, yes A1 is connected to B2 and B1 is connected to C2, yes B1 is connected to C2 and C1 is connected to A2, yes C1 is connected to A2 and keep the arrows at the A1, B1 and C1. So A1, B1 and C1 have to keep the arrows because we are taking supply from A1, B1 and C1. So now we are taking supply from A1. So therefore these are the line voltages, we need a phase voltage. So at the middle point N to this A1 we have to join a vector and this is a horizontal line. So we can say this is the horizontal line, it is lagging. We can say now the LV winding is lagging. LV line phase voltage is lagging the HV phase voltage by 150 degree. So we can say it is a minus 150 degree. So therefore LV winding phase voltage is lagging the HV winding phase voltage by 150 degree. But this is the angle. The angle is nothing but the phase voltage between the A2N and A1N is nothing but 150 degree. But if you go for the sign convention, it is minus 150 degree because it is a lagging in nature. It is a lagging in nature. So here always I have already told you we have to fix our HV winding phasor at the 12 o'clock and LV winding phasor we have to shift it as per the convention. So here it is lagging now. So it is lagging means it has to be downward. So therefore it is 150 degree means it is a 5 o'clock. So it is a 5 o'clock. So HV winding phase voltage is lagging now. See LV winding phase voltage is lagging the HV winding phase voltage by 150 degree means it is a 5 o'clock. So you can see this one is very simple. As you can see the line voltage of the star connection by line voltage of the delta. Line voltage is equal to root 2 times the phase voltage of the star connection by line voltage is equal to phase voltage in the delta connection. So phase voltage of star by phase voltage of delta is nothing but is a ratio of the number of turns of the N1 by N2. So we are going to get root 3 into N1 by N2. So take this important note. Secondary is delta connected. So secondary is delta connected. So we get 3 harmonic currents in phase. So we are going to get 3 harmonic components in a phase and flux is pure sinusoidal and EMF is pure sinusoidal. And what I told you, secondary is basically delta connected. So we are going to get 3 harmonics in the So we are going to get three harmonic currents only in the phase currents. So we are going to get only three harmonic components are going to present in the phase, but not the real phase harmonics or harmonics. So in the phase currents we have only three harmonics, but not the real phase harmonics or harmonics. So therefore, if in current three harmonics are there, means in flux there will be no three harmonics. So we can say flux. So flux will never have three harmonics. So therefore we can say it is a pure sinusoidal. As the flux is pure sinusoidal, so EMF is also pure sinusoidal, because EMF depends only on the flux nature. When the flux is sinusoidal, the EMF is also pure sinusoidal. So now we will discuss about the star delta minus 30. So minus 30 means, simply we can say that minus 30 means it is also called as the 1 o'clock. It means that the low voltage winding, the low voltage phase voltage is going to lag the high voltage phase voltage. So high winding phase voltage. So simply we can say that low voltage phase voltage is going to lag the high voltage phase voltage. So high winding phase voltage. So now we will see here. So it's a star delta. It's a star delta. So input. So we can say this is the star connection and this is the delta connection. So you can see clearly this is A1, A2, B1, B2 and C1, C2. So we are going to connect all the A1, B1, C1 to a common point which is called as a neutral, and from A2 we are going to take it outside as A, from B2 we are going to take another terminal B, from C2 we are going to take another terminal as C. So this is for the input side. So we are going to give supply for this A terminal, B terminal and C terminal. So here we are going to do the delta conversion, means the delta connection. So from A1 to B2 we are going to connection, from B1 to C2, and then from C1 to A2 we are going to give the connection, and we are going to take the supply from A2, B2 and C2. So now I am going to draw the vector diagram or the phasor diagram of this star connection and also this delta connection. So if you see clearly, this is A1, A2, so A1, A2, this is B1, B2 and C1, C2. As A1, B1 and C1 are going to make a common point, they are going to connect to a common point which is called as the N. So I am going to join three vectors and I am going to call it as the point N. And we are going to give supply to the A2, B2 and C2. So we are going to so you have to give the arrows at the A2 and B2 and C2. Similarly, for this one, so this is A1, A2, this is B1, B2. So I just shifted to the upward, I am going to get B1, B2 and the C1, C2 in this fashion. So I shifted here, we are going to make a triangle. So you can see clearly that A1 is connected to B2, yes, A1 is connected to B2, and B1 is connected to C2, yes, B1 is connected to C2, and C1 is connected to A2, yes, C1 is connected to A2. So we got a triangle now. So now, but we need the phase voltage, not the line voltages. So from the middle point, we have to take the neutral voltage. So you can see clearly for A2, from A2 we are going to take the supply. So I will going to draw at the point A2. So you can see clearly this is horizontal line and this is going to lag by 30 degrees. So therefore, we can say that the low voltage, the low winding, or we can say the low voltage winding is going to have a phase voltage which is lagging the high voltage winding. So you can see clearly it is lagging by 30 degrees. So therefore it is called as the 1 o'clock. So you can see clearly that the angle between them is 30 degrees, but simply we can say that it is lagging. It is lagging. Which one is lagging? The low voltage phase for the low winding, the low voltage phase winding. The phase voltage is going to lag the high voltage phase winding. So therefore phase voltage. So therefore here we can say that simply, see I have already told you high voltage means we are going to represent by a minute hand, and the low voltage means we are going to represent by the hour hand. So minute hand is always 6 o'clock to it is always fixed to the 12. So here the phase voltage, the low voltage phase voltage is going to lag this voltage by 30 degrees. So therefore we can say the time is 1 o'clock. So therefore this is the thing. So we can say the phase voltage of the low winding is lagging the phase voltage of the high winding. So you can see clearly it is lagging by minus 30 degrees. So now we are going to discuss the star delta plus 150 degree, or it is also called as the star delta 7 o'clock. So plus 50 means simply we can say that the phase voltage of the low winding is leading the phase voltage of the high winding. That is the meaning of this one. So therefore plus 150 means we can say it is a 7 o'clock. So here we are going to give a star connection, here we are going to give a delta connection. Because you can say clearly this is A1, A2, B1, B2, C1, C2. So A1, B1 and C1 we are going to give a common, we are going to connect together to a common terminal. It is called as the N. And we are going to give supply to this A2, B2 and C2. And here we are going to go for the delta connection. So you can see clearly now A2 is connected, A1, A2, B1, B2 and C1, C2. So A2 is connected to B1, B2 is connected to C1, and C2 is connected to A1, and I am taking supply from A1, B1 and C1 as terminals A, B and C. So now I am going to draw the phasor diagram for these connections. So for this one, A1, A2, B1, B2, C1, C2, as A1, B1, C1 are connected to a common point, which is called as a neutral. So I am going to join these three vectors to a common point as N, as we are giving supply to A2, B2, C2. So keep the arrows at the A2, B2 and C2. Similarly, here I am going to draw the phasor diagram for this delta connection. So you can see clearly this is A1, A2, this is B1, B2. So I am going to shift here. This is C1, C2. I am going to shift in this way. So therefore, we are going to get connection in this manner. So here you can see clearly A2 is connected to B1 and B2 is connected to C1. So B2 is connected to C1 and C2 is connected to A1. So C2 is connected to A1 and we are taking supply from A1 and B1 and C1. So keep the arrows at the A1, B1 and C1. So you are going to get a line voltage of vector. But we want the phase voltage. So therefore take a neutral point N and draw a line because we are taking from A1. So therefore join a line up to A1. So now you can see clearly and draw a horizontal line. So you can see clearly this is going to lead. The phase voltage of the low voltage is going to lead the phase voltage of the high voltage by 150 degree. So this is the reference vector. So therefore it is leading by 150 degree. So therefore hour hand is going to lead the minute hand by 150 means it is a 7 o'clock. So you can see clearly the angle between the A2N and A1 is nothing but 150 degree. But if you go for sign convention, it is minus 150 because you can see I have already told you the high voltage phase, the high winding, the high voltage winding, the phase line to neutral voltage or phase voltage is represented by the minute hand, whereas the low voltage winding, the phase to neutral, the line to neutral voltage or phase voltage is represented by a minute hour hand. So therefore the time is now 7 o'clock. It is leading. So you can see clearly the phase voltage of the low voltage winding is leading the phase voltage of the high voltage winding. So you can see clearly the time is 7 o'clock. So now if you want to find what is the line voltage of star connection by the line voltage of delta connection, because if you want to find the ratio, the line voltage of star connection by line voltage of delta connection is equal to line voltage of star connection is equal to root 3 times the phase voltage of star connection by the line voltage of delta is equal to phase voltage of delta. So therefore this is nothing but N1 by N2. So root 3 into N1 by N2 you are going to get this one. So we get 3 harmonic components in phase currents of delta. So we get 3 harmonic components in the phase currents of delta because delta connection is a closed circuit. So therefore I have already told you whenever there is a closed circuit or is there any path to ground, definitely 3 harmonics are going to get present. So when 3 harmonics are present, definitely there is no chance for 3n plus or minus 1 harmonics. So therefore we can say simply we get 3n harmonic components in the phase currents of the delta, but no 3n plus or minus 1 harmonics are not at all going to present in the phase currents. And if it is not there means in flux it has to be, if 3n harmonics are present in current means definitely 3n harmonics are not going to present in the flux. So therefore we can say flux is said to be pure sinusoidal and EMF is pure sinusoidal and the EMF is pure sinusoidal because EMF is a function of flux only. If the flux is sinusoidal, definitely EMF is also purely sinusoidal. So this is the concept that you always have to remember. So now we are going to study the another concept which is called as the delta star connection of plus 30 degree. So plus 30 degree, it means that what is the meaning of plus 30 degree? I have already told you. So therefore the phase voltage of the low voltage winding is going to lead plus 30 degree by the phase voltage of the higher voltage winding. So therefore we can say it is a 11 o'clock. So it's a delta and it's a star connection, delta star connection. So you can see clearly we are going to give delta connection and here we are going to give the star connection. This is A1, A2, P1, B2, C1, C2. So here we are going to give the delta connection in this manner, A1 to B2, B1 to C2 and C1 to A1. So we are going to give supply at the A2, B2 and C2 as A, B, C. Here we are going to go for the star connection. So you can see clearly this is A1, A2, B1, B2 and C1, C2. I am going to do the common connection of this A1, B1 and C1 to a common point. It is called as a neutral. And I am going to take the supply from this A2, B2, C2 as A, B and C respectively. So now I am going to draw the phasor diagram for this delta connection and also this star connection. So now as I already told you, this is A1, A2, B1, B2 and C1, C2. So here A1, A2, and B1, B2, I am going to make it in this manner. So therefore you can see clearly again C1, C2 in this manner. I am going to make it shift like this. So now A1 is connected to B2, so A1 is connected to B2, and B1 is connected to C2, yes, B1 is connected to C2, and C1 is connected to A2, so therefore we are going to get in this manner. And also we are going to do supply to this A2, B2 and C2, so keep the arrows at the A2, B2 and C2, A2, B2 and C2. So this is the diagram we are going to get. This is basically line voltages, but we need the phase voltage, means from the center point take a neutral and draw a line up to this A2. So therefore here we are going to get like this one. This is the phase voltage and here is the horizontal line. So it is going to, this is called the 30 degree. So now I am going to draw for this one. So here also A1, A2, B1, B2 and C1, C2. Here A1, B1, C1 are going to mix to a common point which is called as the neutral N. And we are going to take the supply from the A2, B2 and C2. So keep the arrows at the A2, B2 and C2. So now you can see clearly that this voltage, so this voltage is going to lag by this voltage by 30 degree, or you can say this is going to lead this voltage by 30 degree also we can say. So low voltage phase winding, the low winding phase voltage is going to lead the high voltage phase voltage by 30 degree. So therefore we can say it is a 11 o'clock. So the angle between the phase voltage of the delta connection and the star connection or HV and LV, we are going to get 30 degree. So therefore I have already told you the high voltage winding is represented by the minute angle and the low voltage winding is going to represented by the hour hand, and also the minute hand is always fixed to the 12 o'clock, and this low voltage winding is going to lead by 30 degree. So therefore we can say it is a 11 o'clock we are going to get. So now we are going to discuss about the another connection which is called as a delta star minus 150 degree, or delta star we can say it is a 5 o'clock. So therefore minus 150 means simply I can say that it is the phase voltage of the low winding is going to lag the phase voltage of the high voltage winding. That is the meaning it is called as the 5 o'clock. So therefore now delta connection and star connection. So A1, A2, B1, B2, C1, C2. So A1 is connected to B2 and B1 is connected to C2 and C1 is connected to A2. So we are going to give supply to this A2, B2 and C2 as A, B and C. And here we are going to go for the star connection. So you can say clearly this is A1, A2, B1, B2 and C1, C2. So we are going to do the common connection of this A2, B2, C2 as a common point as the N, and we are going to take the supply from this A1, B1, C1 as the A, B and C. So now I am going to draw the phasor diagram of this delta connection and also this star connection. So you can say clearly this is A1, A2, B1, B2. I have shifted in the upward direction. C1, C2, I have shifted in this direction to make a triangle. So therefore you can see clearly A1 is connected to B2, yes, A1 is connected to B2, and B1 is connected to C2, yes, B1 is connected to C2, and C1 is connected to A2, and C1 is connected to A2. So we are going to get a triangular shape of line voltages, and we are going to give the supply to this A2, B2 and C2. So here also we are going to keep the arrows at the A2, B2 and C2. But we want the phase voltage, so therefore keep a center point as N, and we are going to go for this A2 terminal. So therefore draw a straight line up to A2. So it is called as like this. So this is called as a reference phasor, reference horizontal line. So this is the angle between the reference phasor from here to here, this 150 degree. And for this now I am going to draw the phasor diagram. So you can see clearly A1, A2. So A1, A2 here I have shifted in this direction, and B1, B2 means I have shifted in the upward direction. C1, C2 in this direction means I have shifted downward. So therefore here A2, B2, C2, A2, B2, C2 are connected to a common point, and we are going to name it as the neutral. And here we are going to take supply from this A1, B1 and C1. So therefore you have to keep the arrows at the A1, B1 and C1. So if you see clearly the neutral voltage, the phase voltage of the low voltage winding is in this direction, and here it is in this direction. So therefore we can say the angle between them is 150 degree. So this voltage, we can say this voltage is going to lead this voltage by 150 degree. So therefore simply we can say this is lagging this voltage by 150 degree. So that is the reason we can say it is a 5 o'clock. So simply we can say that the phase voltage of the low voltage winding is going to lag the phase voltage of the high voltage winding by 150 degree. So therefore we can say the time is 5 o'clock. Now we can say that the phase angle between the phase voltage of the higher voltage winding and the lower voltage winding is nothing but 150 degree. So here I've already told you the high voltage winding is represented by the minute hand and it is always fixed to the 12 o'clock. It is always fixed to the 12 o'clock. Whereas the low voltage winding is represented by the hour hand and it is lagging the higher voltage phase voltage by 150 degree means we are going to get a at 5 o'clock we are going to get. So this is the thing that we can see clearly. So therefore, now if you want to find what is the line to line delta voltage by line to line star connection, see always the phase voltage and line voltage is same for a delta connection. So V phase by delta by, whereas the line voltage is equal to root times the phase voltage in star connection. So therefore 1 by root 3 into and 1 by L2 we are going to get. So in delta connection, 3 harmonious components of currents are present. So always in delta connection, we are going to get only 3 harmonic components, but not the 3n plus or minus 1 harmonic components. So if the phase current has 3n harmonic components, then definitely flux will never have the 3n harmonic components. So flux will be pure sinusoidal. As the flux is pure sinusoidal, then EMF is also pure sinusoidal because EMF is depending only on the flux. So last one more connection we are going to discuss here. It is called as the delta 2 star 1 o'clock. So 1 o'clock is also called as the minus 30 degree because we can say that simply by seeing it only we can say that the low voltage phase, the low winding phase voltage is going to lag the high voltage phase voltage by 30 degree. That is the significance of this one. So here we are going to give for delta connection and here we are going to give for the star connection. So A1, A2, B1, B2, C1, C2, A1, A2, B1, B2, C1, C2. So this is called as a delta connection. So A2 is connected to B1, B2 is connected to C1 and C2 is connected to A1. And here it is a star connection. So simply we are going to connect this A1, B1, C1 to a common point. It is called as a neutral and we are going to take the supply from this A2, B2 and C2. So now we are going to draw the phasor diagram for this input side and also the output side. So you can see clearly this is A1, this is A1, A2, this is B1, B2, this is C1, C2. So this is A1, A2 and B1, B2 I am shifted in this manner and C1, C2 I am shifted in this manner. So A2 is connected to B1, yes A2 is connected to B1, B2 is connected to C1, yes B2 is connected to C1 and C2 is connected to A1. So C2 is connected to A1 and we are giving supply to the A2, B2 and C2. So keep the arrows at the A2, B2 and C2. So these are the line voltages, but in the phase voltage, so keep a neutral point here and take a line from here to the A2 point. So this is called as the phase voltage of the HV winding. So this angle is 30 degree. So now I am going to draw the vector diagram or the phasor diagram for the star connection. Here also A1, A2, B1, B2 and C1, C2. So now we are going to connect this A1, B1 and C1, A1, B1, C1 to a common point N. So we are going to connect this A1, B1, C1 to a common point as N and we are taking supply from A2, B2, C2. So keep the arrows at A2, B2 and C2. So A2, B2 and C2. So now you can see clearly this is a phase voltage, this is also phase voltage. The angle between them is nothing but 30 degree. So this is going to lag this voltage by 30 degree. So therefore we can say that simply the low voltage phase, the low winding phase voltage is going to lag the high winding voltage by 30 degree. So therefore we can say the phase angle between the phase voltage of the HV winding and the LV winding is 30 degree. I have already told you the HV winding is going to represent by the minute hand and it is always going to fix at the 12 o'clock. Whereas the hour hand is called as a LV winding phase voltage, it is going to lag by 30 degrees. So therefore it is called as the 1 o'clock. So now we are going to discuss the last connection, which is delta 2 star plus 150 degree or delta 2 star 7 o'clock. So this is the delta connection and this is the star connection. This is A1, A2, B1, B2 and C1, C2. So we are going to connect this A2, B1, B2, C1 and C2, A1 and we are going to give the supply of this A2, B2 and C2. And this is the star connection. Here we are going to connect this A2, B2, C2 to a common point. We are going to call it as the neutral point. And we are taking supply from this A1, B1, C1 as the A, B and C. So now I am going to draw the phasor diagram for the input side and the output side. So you can see clearly this is A1, A2, B1, B2 and C1, C2. So this is A1, A2. So B1, B2 I have shifted in this manner and C1, C2 I have shifted in this manner. So therefore we can see clearly A2 is connected to B1, yes A2 is connected to B1 and B2 is connected to C1, yes B2 is connected to C1 and C2 is connected to A1, yes C2 is connected to A1. So we are going to get a like this representation. So we are going to give supply to this A2, B2, C2. So keep the arrows at this A2, B2 and C2. So now But these are the line voltages, but we need the phase voltage. So keep a neutral point at the center and take this point up to A2. So this we can say it is horizontal line. It is having an angle of 150 degree in this direction. Similarly here I am going to draw the phasor diagram for this star connection. So this is A1 B2, B1 B2 and C1 C2. So A1 A2 I shifted in this manner and I got like this. B1 B2 I shifted in this manner, so I got like this. C1 C2 I shifted downward. I am going to get like this. I am going to connect A2 due to C2 as a common point, which is called as the N. So I am going to connect A2 due to C2 as a common point as N, and we are taking supply from A1 B1 and C1. So therefore we can simply say that as we are taking supply from A1 B1 C1, so keep the arrows at the A1 B1 and C1. So now you can see clearly this is the phase voltage and this is the phase voltage. The angle between them is nothing but 150 degree. So now this voltage is going to lead this voltage by 150 degree. So therefore we can say that this voltage is going to lead this voltage by 150 degree. So therefore simply we can say it is a 5 o'clock. So therefore the angle between them is nothing but 150 degree. So this the phase what I told you, the HV winding phase voltage is represented by the minute hand. It is always fixed at 12 o'clock. Whereas the LV winding phase voltage we are going to represent by the hour hand. It is leading by 150 degrees. So therefore we are going to get a 7 o'clock. So now we are going to discuss the different types of connections in a transformers we are going to discuss. So 3 single phase transformers connected to 3 phase load. So by using 3 single phase transformers, we are going to make a 3 phase transformer and we are going to connect to a 3 phase load. So this is a transformer 1, transformer 2 and transformer 3. So it has a primary winding and secondary winding, primary winding and secondary winding, primary winding and secondary winding. So all the primary windings we have connected in a star connection. So all these 3 terminals are going to connect to a common point, and the remaining terminals we are going to take outside and we are going to give the 3 phase supply for these terminals. And here also we are going to go for the star connection. So we are going to go for the star connection, and these 3 points we are going to connect to a common point, and the remaining 3 terminals we are going to take outside and we are going to connect to a 3 phase star connected load. So this is called as a by 3 single phase transformers we are going to make a 3 phase transformers. Input side we have connected in the star connection, and the output side also we have connected in the star connection, and the load is now a 3 phase star connected load. So input we have given a 3 phase balance supply. So we can see the star connection. So a single 3 phase transformer. So now instead of choosing 3 single phase transformers, then we try to make a single 3 phase transformer. So instead of choosing 3 single phase transformers, we try to build a single 3 phase transformer. So like this. So this is the core 1, this is the core 2 and core 3. So you can see clearly this is the core 1, core 2 and core 3. Here we are going to give the primary winding and its secondary winding. Here we are going to give the primary winding and its secondary winding. Here we are going to give primary winding and its secondary winding. So this primary winding is going to generate a flux phi r. This primary winding is going to generate a flux phi y, and this winding is going to generate a flux phi b. So you can see clearly this is the net resultant flux in this middle core, which is phi r plus phi a plus phi b. So as these are phase difference by 120 degree, so net sum is always equal to 0. So therefore this flux is always 0. So in this middle core, the flux is always equal to 0. So instead of this, we can remove this one. So we are going to remove this core because this flux is always 0. So we need to keep this one. So we are going to make this a very simple one. This is called as a very simplified version. So instead of we are going to remove that middle core and we are going to make a simplified version. This is called as a single 3 phase transformer. This is called as a single 3 phase transformer. You can see clearly now there are 3 limbs, and this is the primary winding and its secondary winding. It's a primary winding and its secondary winding. It's a primary winding and its secondary winding. So here we are going to give the supply. Here we are going to give the supply. Here we are going to give the supply, and here we are going to connect to a load, whichever the 3 phase load we can connect. So this is going to generate the flux phi r. This is going to generate the flux phi y, and this is going to generate the flux phi b. So input you can connect in any connection, and the output also you can connect in any connection you want. So it is you can see it is a very simplified version of a single phase, so a single 3 phase transformer. So now we are going to see a star connection. So we are going to basically see the star connection. So you can see clearly star connection means input side we have counted in the star connection, and the output side also we have counted in the star connection of these three single phase transformers. So you can see clearly for the input side, 3 points are we are going to connect to a common point, and we are going to connect as the neutral, and this is the binding voltages which are VAN, VBN and VCN. So therefore this is the terminals A, B and C. Similarly, in the output side also we are going to connect in the star fashion. So with these 3 points we are going to connect to a common point N, and this voltage is VAN, VBN and VCN. So we are going to take the output as A, B and C. So basically we can say it is a star-star connection. See, I have already told in detail regarding the star-star connection. In star-star connection, we can get only 0 degree or 180 degree. So the 0 degree means 12 o'clock, 180 degree means 6 o'clock. All these things we have discussed. So I have already told you 0 degree. See, all this phase displacement means I have already told you this is the phase difference between the phase voltages of the high voltage winding and the low voltage winding. All these things I have also discussed. So we will discuss further. And one more important point is, if you want to go for parallel operation of transformers, I have already told you the 4 important conditions. One is they should have the same voltage ratings, and the same polarity should be connected in the primary and secondary, and the phase sequence of the transformers, 3-phase transformers should be same. If the first transformer is star-star, the second transformer should be also star-star. And in the star-star also, the 4th condition is they should have same phase sequence. So the same phase sequence and same phase shift means if the star-star to 0 degree, the second transformer should be also star-star 0 degree only. So this is the thing that you always have to remember. This is called as a delta-delta connection. So delta-delta connection means the input we are going to connect in delta, and output also we are going to connect in delta. So this is the transformation ratio of 3 single phase transformers, so 1:n for each and everything. So here we are going to connect in a delta fashion. So you can see clearly this is like a delta connection, and we are going to take this common point from terminals A, B and C. We are going to give the supply, and here also we are going to do the connection in a delta fashion. So you can see clearly here also we are going to do a delta connection. Then we are going to take the supply from these terminals. Like this we have to connect. So like this we have to take from the common points, you have to take the supply. Here also you have to connect like this, and you have to take the cross supply from this common terminals. So in the delta connection also I have already told you there are 2 things are going to possible. In delta you can get 0 degree or 180 degree. 0 degree means it is nothing but it is a 12 o'clock, and 180 means it is a 6 o'clock. I have already told the 0 degree simplifies that these are the phase difference between the phase voltages of the HV winding and the LV winding. All these things I have already told you. So this is basically delta to star conversion. So delta to star conversion. So you can see clearly this is the delta, this is star. So now this is the A terminal, B terminal, C terminal. We are going to use supply here, and we are going to give supply to the load V1. And I already told one important point. In delta star you can get either 0 degree, you can get either 30 degree or plus 30 degree or minus 180 degree or minus 30 degree plus 180 degree. You can get anything that you want. These 4 things are possible in this delta star conversion, and I have already told each and everything. This degree is nothing but it is a phase difference between the phase voltages of the LV winding and the HV winding. So now we are going to discuss the star delta conversion. So this is the star connection and this is the delta conversion. So this is the star connection and this is the delta connection. So you can see clearly. So now what I am going to do basically here, I am going to give a line connection of VAB. So phase voltage is VAB by root 3. This 1:n. So therefore each turns ratio is 1:n. So therefore the voltage is going to have phase voltage of n into VAB by root 3. So n into VAB by root 3. So therefore line voltage is equal to phase voltage. So this is the thing. In star delta I have already told you, in the star delta you can get plus 30 degree or minus 180 degree or minus 30 degree or plus 180 degree. All these things I have already told you. The open delta. So this is the basically open delta connection now we are going to study. Before that let me study about the delta connection. So this is the 3 single phase transformers. We are going to connect the input in delta and output is also in delta. So you can see clearly like this we are going to connect, and then we are going to supply to this common terminals. Here also we are going to connect in this manner, and we are going to take supply from this terminals. So it is called as a delta connection. Suppose if one of the transformer got some fault, then we have to remove it from the operation. So what is going to happen if you are going to remove one of the transformer, then its overall rating is going to get decreased. Then the new kV rating of this open delta is equal to, we can say it is 1 by root 3. So 1 by root 3 times of the kV rating of this delta delta. 1 by root 3 is nothing but, which is nothing but 57.7% of the kV rating of this delta delta connection. So now let third transformer is damaged, so we are going to disconnect it. Now you get a open delta connection. Open delta means we are going to remove one transformer because it has got some damage, so we are going to remove it. So we are going to remove it, but still we can give supply to the load, but its overall kV rating is going to get decreased. It can't handle more than that. This is the transformer that I have removed it. So this is the connection we are going to get. Now we can rearrange into a small amount of fashion, like equivalent. We can rearrange this one into small equivalent, which is, so after doing rearrangement, we are going to get like this. So this is the rearrangement we are going to get. So now you can see clearly this is the equivalent circuit we are going to get after this removing of the third transformer. So this is the circuit we are going to get after removing the third transformer. So you can see clearly this is plus or minus VAB, this is plus or minus VBC, this is plus or minus VAB, this is plus or minus EBC. So this is capital A, capital B and capital C. So here capital A, small b and small c. So you can see clearly still it can supply the load, but its kV rating is going to get decreased. See, in open delta connection, power rating will reduce by factor of 1 by root 3 or 57.7%. So therefore, the new kV of this open delta is only 57.7% of the kV rating of this delta delta transformer. So these are the line voltages. So now we will discuss about the Scott connection. So what is the help of Scott connection? With the help of Scott connection, we can transform a 3-phase supply to 2-phase supply or 2-phase supply to 3-phase supply. This also I have already discussed in the previous class only. So we are going to use two transformers. One is called the primary transformer and other is called the teaser transformer. In the teaser transformer, the primary winding we are going to change the number of turns so that we are going to get the balanced 2-phase supply. So we can generate 2-phase voltage from a 3-phase voltage or generate 3-phase voltage from a 2-phase voltage, vice versa. You can generate a 3-phase voltage from 2-phase voltage or from 2-phase voltage to 3-phase voltage. You can generate with the help of the Scott connection. I already told you that in this Scott connection we are going to use two transformers. One is primary transformer and other is called the teaser transformer. And one more important point I have already told you, if you connect a balanced load, if you keep the number of turns in the primary winding of teaser winding, which is n is equal to 3 by 2 times of n1, then definitely we can say that if you give a balanced supply, we are going to get a 2-phase balanced voltage. But if you connect a balanced load, then the voltages are balanced, input voltages are balanced, output voltages are balanced, and the output currents are balanced, and the input currents are also balanced. But if you give an unbalanced load, then we can say input voltages are balanced and the output voltages are balanced, but the output currents are unbalanced and the input currents are also unbalanced. This is the meaning of this one. So by this lecture, we have successfully completed all the transformers, important concepts and their formulas in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe to the YouTube channel, and don't forget to press the bell icon button. So whenever we upload new video, the direct notifications come from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely improve all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.